Topic 3 is systems of linear equations. So what I'm building up to is I want to be able to solve problems like this. So I have 3 equations in 3 unknowns. So the unknowns are x, y, and z. And then each row here is 1 equation. And I want to find x, y, and z that simultaneously satisfy all 3 of these equations. So there are 2 ways I can look at this if I try and translate this into vectors. So I can look at something called the row picture. So that's trying to describe each one of these rows. And if I do that, what I end up with is the dot product. So I'd have the dot product of the coefficients. So there's an invisible 1 here. So if I just say x, I really mean 1 times x. So that's where this 1 comes from. So the first row is 1, 2, 3 dot xyz is equal to 6. Second row is 2, 5, 2 dot xyz is equal to 4, and so on. And it turns out I can also do this using a column picture. So I can also think of this as x times 1, 2, 6, y as 2, 5, minus 3, and z times 3, 2, 1. So it's just these same numbers are the coefficients here. So I can think of this either as dot products that give me the rows, or I can think of this as a linear combination of the columns of my coefficients. And so the problem this is trying to describe, let's see. So you can see there's sort of this dark point here. And each one of these equations in the row picture, it's describing one of these planes. And so it's really difficult to try and put 3 planes onto one picture. Even this one, I failed miserably trying to do my own artwork, so I just copied this out of the book. And even there, I still can't really convince myself what direction this plane here is supposed to be tilting. You know, sometimes it goes from looking like this to looking like this to me. But the point of this is supposed to be I have these 2 planes, and the space where they intersect is going to be this black line here. So if I have one point that's kind of like this and one point that's like this, where they intersect is going to be described by a line. So the intersection of the first 2 planes will give me a line. So I've gone from having sort of 2-dimensional objects. So these 2 planes, they're 2-dimensional objects that exist in 3 dimensions. When I intersect them, I now have a 1-dimensional object, so this line that exists in 3 dimensions. And then to solve my problem, so to finish solving my system of equations, I need to intersect that line with the 3rd plane. And so if I have a plane and one line, it's going to hit at just a single point, and that point is going to be the value of x, y, and z that solves my system of equations. So I want to now try, so that's sort of the row picture. So remember, the rows were giving me equations of planes, and those planes then were giving me this picture, and that was giving me one approach for solving this problem. And now I'm going to also try and consider solving it using the column approach. And so to do that, I'm going to start by stacking rows or binding columns. So I can either think of the rows as being the coefficients from each equation, or the columns of being the coefficients for each variable. So if I stack the rows, I put the coefficients for the 3rd equation on bottom, 2nd equation in the middle, and the 3rd equation on top. Or I can take all of the x coefficients and put them in the 1st column, y coefficients go in the 2nd column, z coefficients go in the 3rd column. Sort of the nice thing about this is we get a duality. So it doesn't matter which approach I take, I'm going to get the same answer. So quite often, like in statistics, it turns out that looking at the columns of a matrix makes calculating statistical properties of estimators very easy. And looking at the rows of the data in a matrix makes plotting the data. So actually looking at it, with your eye, very easy. So you can use the rows to make plots, and you can use the columns to do mathematics. But because you're really doing the same thing, regardless of whether you try to use the row problem or the column problem, both of those are going to be descriptions of the same actual problem. So if A is my coefficient matrix, then I can write my system of 3 equations and 3 unknowns like this. So I have the coefficient matrix times a vector of unknowns, and that's going to equal a vector of the right-hand side. So these were equations like something, ax plus by plus cz equals d. So these are these values d. They go on the right-hand side here in a vector called b. And so you can recover pretty easily the row picture here. So I just have 1, 2, 3 dot xyz equals 6. That's going to give me the first equation. And I can repeat that for the second or the third row. Or I can say x times 1, 2, 6 plus y times 2, 5, negative 3 plus z times 3, 2, 1 equals 6, 4, 2. And that gives me the column picture of the problem. And so we can think of this as the left-hand side multiplies A times the unknowns V to get B. And so what we want to move towards now is having some sort of multiplication rule for matrices and vectors that's going to make sense out of this. So the properties we want it to have are it has to give this linear combination for the column picture, and it needs to give me the row picture. So I need the dot product here. This row of this matrix times this column vector of unknowns, that needs to be a dot product. So I can represent this as AV being just row 1 dot V, row 2 dot V, or row 3 dot V. Or the column picture, A times V, that's just going to be, so X here was the first component of my vector V, Y was the second component, and Z was the third component. And so just some examples here. So if I have 1, so 100.456, that's going to equal 4. 100.456 again is going to equal 4. And 100.456 is going to equal 4. So that's multiplying by this matrix A, just plucks this first value out and puts that in the answer. Another matrix, so this matrix has a special name, it's called the identity matrix. If I have ones down the diagonal, so the diagonal is where the row is equal to the column. So here I'm in the first row and first column. Here I'm in the second row and second column. Here I'm in the first row but the second column, so it's not on the diagonal. So if I have ones down the diagonal and 0 everywhere else, then that's just going to give me the same vector back. So I'd have 100 times 456. That's going to just pluck out this 4. Then 010 times 456. That's going to take the 5. And 001, that's going to take this 6. So suppose I have this system of equations, so 3x minus y equals 3, and x plus y equals 5. I can write that in the matrix form as a coefficient matrix times an unknown vector xy is equal to the vector 3, 5. And I can draw 2 pictures of this now. So as long as these are 2 equations and 2 unknowns, it's easy to draw. So the row picture, this is probably how you want to think about this. So each one of these rows determines a line in the xy plane, and then the answer is just going to be where the 2 lines intersect. So I drew these 2 lines, and they intersected at the point 2, 3. And so you can see if I put in 2, 3 here, I get 6 minus 3 is equal to 3, and 2 plus 3 is equal to 5. So that is actually the solution to the system of equations. I can also draw the column picture. So this one's a little bit trickier to see, but the columns are 3, 1, so that gives me my first column. And so this arrow here, labeled column 1, I go over 3 and up 1, so this is column 1. Column 2 is negative 1, 1, so that's this vector here, so negative 1, 1, and it's labeled column 2. And then I'm looking for a linear combination, so I'm looking for something times column 1 plus something times column 2 that's going to equal 3, 5. And so you can visualize that. So if I want to get, if I have to follow these two directions, so either this direction or this direction, and I want to get to the point 3, 5, then what I need to do is go 2 times column 1, and that gets me to this point. And then I'm going to add 3 times column 2, that gets me up to this point. So this point up here, which is 3, 5, I can describe that as 2 times column 1 plus 3 times column 2. And so 2 times column 1 plus 3 times column 2, so that gives me the vector 6, 2 plus the vector negative 3, 3. So 6 minus 3 gives me 3, and 2, 3 gives me 5. So that gives me the same answer whether I try and do this using the row view or the column view. And then both of those are representations of this matrix form of the equation. So some properties of systems of equations. So most of the time, if you have the same number of equations in unknowns, there's going to be one solution. So that means, you have a plane like this, a plane like this, that determines a line, and then you maybe have a plane like this, and wherever that line hits the third plane, that's your solution. But of course things can go wrong, so you could have 2 planes that are actually the same plane. So imagine if I took the equation of a plane and just multiplied both sides by 2, every point would still be, the points that satisfy that are going to be the points in the same actual plane. Or I could have 2 planes that were parallel, and so there would be no intersection between those. So there may be no solution. So if 2 lines are parallel, and basically my interpretation of a system of equations is where do these 2 lines intersect. If the 2 lines are parallel, we'll get no solution. Or if you have 2 equations that look different but are actually describing the same line in the plane, then you have infinitely many solutions. So any point on that plane will satisfy the equation of both lines. Sorry, any point on that line satisfies the equation of each line.